Okay, Selina is also there. 12 people. We are missing one. Let's count. 1, 2, 3, 4, 5, 6, 8, 10, 11, 12, 13. Okay, 13. So only one people we are missing. But I think it's okay. I think we shall start now. Okay. So we start with the first presentation of today, given by Mr. Dalal about Rutherford backscattering principles and applications. And please start your presentation, Mr. Dalal.
So wish you all a very good afternoon, and let's have a discussion on Rutherford backscattering principle and its applications. As we have already seen, last time we saw that according to Thomson model, this positive charge is scattered all over this atom, and somewhat electrons are also embedded in this atom, and they are also randomly spaced or randomly put on different places. But later on, Rutherford came up with this model, and this positive charge is concentrated at one point. In this space, this is not scattered uniformly, but it is concentrated at the center and it's very dense. Again, the electrons are randomly spread all over. So this was the gold foil experiment which was carried out. Alpha rays comes, strikes to the gold foil, and different scattering patterns could be analyzed. If we go on atomic scale, if we see this layer, we can see alpha rays are coming, and most of them are going straight. Why straight? Because now we know that most of the space is empty, and these are just interacting with the electrons, and those who are interacting with the nucleus, they are reflected back or they are deflected to a big angle. So this is basically the backscattering. So far we just discussed the analytical part and we just analyzed the things. But now we move on to more of calculation part, how these rays are coming, how they are striking, and we are more interested into the calculation part. What more we can find out from this experiment. So here we have the principles of RBS. Light rays with some energy or in mega electron volts comes, strikes to this specimen. These are the atoms, maybe one element or a complex matrix of different elements it can be. They collides elastically and they are scattered back. These are scattered back particles, and we analyze these particles, we detect them, and we see the energy, like how the energy is lost by these particles. They come, strikes, and after these scattered back particles lose their energy. So we analyze this spectrum actually. And most important here is like the central force field. This is nothing but when we have a force in a line. So if a force is pointing towards a point or away from a point, then it is called a central force field. Also, like these particles are not these are just the charges which are interacting. So this is some charge of this atom and this is some charge of this atom, and they are just interacting. So what kind of interaction is taking place? That's Coulomb interaction. And the most beautiful part of the presentation is most of the things are classical mechanics, so these are very easy to understand. So in order to penetrate through some depth, we need a specific energy which should be in mega electron volts, otherwise it won't penetrate and will lose the beam, or we just absorb the beam. So this is the experiment setup for RBS. Everything is inside the vacuum. This is some target, we don't know. This can be any matrix, this can be a single element, this can be coating, this can be different layers of elements. But what we have monoenergetic beam of ions. Here we are assuming as helium beam, it can be any other beam also. It comes, strikes to the surface, and some beams are scattered back. Some of them will go straight, as we know most of the parts is empty and they can pass through, but which are scattered back, we detect them through the detector. So this is the kinematics of elastic collision. All the collisions are elastic. This is collimator. Only fine pencil beams comes strikes to this atoms of the matrix, and they are reflected. We are analyzing now the energy. So initially we only have the energy of the beam ions. So this is kinetic energy, half mv square. But after it collides, it's distributed among itself and the atom of the matrix. So here is the expression for that. And if I go on to the momentum, so initially we have a momentum only because of the ions of the beam, but later on it is also distributed among the beam ion itself and the atom of the matrix. If I take the components, if I split the velocity components in x-axis and y-axis, this is the expression we get. Initially we had only in the x-axis, so we don't have any component of momentum in y-axis, and this is the way this will be distributed. This momentum will be distributed among the two particles which are colliding. So after we have seen the kinetic energy and the momentum conservation, we come up to the kinematic factor. What this kinematic factor is? Kinematic factor is, it's the ratio of energy after the collision with the nucleus and initial energy with which the particle is bombarded onto that. So this is the expression we have for the kinematic factor. If I see at a particular angle theta, this is scattering angle 170 degree. We have this table. Here we have the kinematic factor for M2. M2 means the atom of the matrix to which the ions are colliding, and this is the mass. For different ion beams, we have this values of kinematic factor. Now, if I combine all these things all together in one slide, this is I came up with. So this is this I have drawn. Here we have on a particular substrate we have different coatings, or there could be anything, different metals, layers with different thicknesses. It's there. So here is the surface. This could be considered a first case where a beam of ions is coming. It strikes to the surface and it goes back. Again, this is the scattering angle, and here what is happening? This everything is in vacuum itself. So E naught energy comes, strikes to the nucleus, goes away, and according to the kinematic factor, energy is lost. We are analyzing this energy through the detector at this particular angle theta, and that way we are able to plot the graph. We see the spectra and we analyze which element it would be. Because we know the initial energy, we know the final energy, we find the kinematic factor, and with the help of kinematic factor, we find the atom. So leaving on to the second, third, and fourth, we discuss the fifth one. Now how the things are going on here. This energy beam of E naught comes, till here the energy is E naught. Again it starts to penetrate into the layer 1. Now while it's penetrating, it has to lose some energy because it's interacting with the electrons of this specific element. Some energy is lost here. Again some energy is lost in part 2. Again some energy is lost in part 4. And now it comes with that the component of energy which is left with it. Now this energy is considered, and this energy is considered, which will contribute to the kinematic factor of this particular atom. Again it comes back, and again the loss of energy this time will be more than the initial while it was coming, because here we have this angle, scattering angle, and this will be length would be even greater than the initial length. So now the lost energy in this particular matrices will while retracing the path will be more. So here we consider that, and here again outside we have a detector. So we analyze things again with the detector and put the spectra. On the spectra we see what kind of composition it could be. So this we have a spectra. Here let's see from here, 2.5 mega electron volt of helium atoms. These are helium atoms, ion beam. This comes, strikes to this complex matrix, it goes back. This is the energy even we get. This is the energy plotted over here, and here is the substrate, and on this we have copper, silver, and gold. Now we don't know how it is or which elements are these were on this. We just have this information, helium ion with a specific energy and the reflected energy of it. If I start from here, so kinematic factor for the elements which are higher in number, which are have higher atomic number, they have kinematic factor bigger. So kinematic factor is big, then E1 will be big. So we analyze this and plot it. We could say it, and now again we can even distribute, like for copper we have its isotope 63 and 65. Because there is an energy gap and different kinematic factor, so we just find like in this matrix even the isotopes of copper were present, so we can actually conclude like what kind of matrix and what all elements were present onto this silicon substrate. This is this has high precision and high sensitivity. Complex matrix is not affected. This matrix independent, any kind of matrix can be used. It is very fast, non-destructive, and multi-element depth concentration profiles can be analyzed with this. Now typical applications, as we have already seen, absolute thickness of coating could be analyzed with the spectra, surface interface contamination, interdiffusion kinetics of the thin films. Kinetics plays with something in motion, so we have atoms which are diffusing actually, and we could analyze into the thin films. So 1 minute to go. I just have a doping of some elements, so we can also find out like what kind of doping, and we can also analyze things into that composition, contaminant control. Okay, and the last part is estimating the size of the nucleus. So where we have seen the Coulomb interaction, and what is happening, like for the matrix it's at rest, and these particles, ion beam particles, are coming with some energy, but as they come close, they will also stop at some point. So all of the kinetic energy is it is converted to the potential energy. If I assume some kinetic energy 4 mega electron volt, it is completely transferred to the potential energy. If I put in the expression for potential energy, which is k q1 q2 upon r, I find a factor r, which is the distance of closest approach, and from that we can conclude what could be the possible size of the nucleus, in what terms or in which power factor it could be. So this is also a good way to estimate the size of the nucleus, and that's all. These are all references I used, and I think I was on time. Thank you so much for your kind patience, and now I'm open for questions.
Thank you very much, Mr. Dalal, for your nice presentation. It was very impressive to see your own picture and the demonstration about the processes inside. So thank you. And, the session is now open for questions, please, the audience. No questions about? Then may I start with the first question?
Yeah, please, Professor.
You demonstrated the energy spectrum slide, slide 11, yes, 11. So you can determine different type of isotopes, you can determine different elements as well. But what's about the quantity?
Okay.
Can you say something about the quantity of this?
Okay, perfect. So, what is happening here? This helium ions are coming, and now here I have a screen, or here I have the surface of the coating. So this particle comes, it strikes to the surface. This could be a possible reason that it strikes onto the very surface nucleus, goes back with a maximum energy. So this energy is analyzed. Again, if I take a situation here, this beam comes, penetrates all through this distance, and here inside onto the quantity, like what will be the thickness of this particular layer, it comes inside, it's continuously coming in contact and interacting with the electrons. So part of its energy is already lost, and this part of energy is analyzed with the kinematic factor to the striking atom of this layer, which is much behind into the thickness of the material or the coating, and it comes back. While it retraces its path, the path length will be depending on the scattering angle theta, and again some part of energy is lost in these two processes while interacting with the electron, and this energy is analyzed with the detector at that particular angle, and we put the spectra, and in spectra we could analyze what would be the thickness of it. For here, like silver atom, actually for this particular case we had an isotope of silver, but we could not analyze this. Like we could see for copper the difference of like it's 17 kilo electron volt, but for this particular detector, the limit was 15 kilo electron volt. We could not see the difference of 15 kilo electron volt for silver, so we could not resolve the issue of isotopes for silver. We could only resolve the issue of this copper. I hope I answered your question, Professor.
Okay, thank you. There are further questions to Mr. Dalal.
Yeah, please.
Everything seems to be clear for everybody. It's a nice procedure to use, and you demonstrate also on one of your last slides possible applications. Do you have also any results or any pictures of one of these demonstrations of these applications?
I could explain it because the time limit was so I could not put it in PPT, but I have everything. Like I know all of these applications, and I can explain anything and everything out of them. If you want, I can explain any one of them in complete elaborations. I have it, like I have like presentation, but already it was like 14 slides, 15 slides, so I just left that out.
That's fine. That's absolutely fine. You're also just in time. That's not the point. Sometimes it might be helpful if you have one or two slides in the back. So you know. So if people are asking for, let's say, type of application or demonstration about, then you can switch on the backup slides.
Oh, next time I'll keep in mind.
It's not. It's fine, of course. So, thank you very much for your presentation. It was really nice to see, and I have the impression you understood the technique very well, and from the fundamentals of physics, you know very well about the elastic collision and so on. So, thank you. Now we have to vote. I have to start the live voting now to see what the general impression was. So please switch on your Ilias folder and go to the presentation and discussion techniques evaluation button, and now I want to start the live voting for everybody. So the first question is given now.